So as we're looking now to Riemann sums, we're going to be building on the upper rectangles, lower rectangles, using the limit as n approaches infinity of the number of rectangles. We're going to be building on that because actually what we've dealt with so far has had certain restrictions on the types of functions we were able to work with, okay? And the mathematician, Riemann, okay, that we get the name from here, actually was able to generalize the process that we've been talking about that had existed before he was around, before he started doing his stuff. He generalized it so that there weren't as many limitations and so that we were able to find areas with a broader range of functions than we were before, okay? So, and we'll see a couple of those things as we move through here. The first of these, though, that Riemann was able to identify is the fact that it's not necessary to have subintervals of an equal width, okay? Now, when we were doing that delta x was always b minus a over n, we were assuming, or we were forcing them all to have the same width, okay? Riemann recognized that as you make the intervals, or as you make the rectangles more and more and more, as n approaches infinity, what's going to happen to the width of those rectangles? What? No, other way. Yeah, they're going to get smaller. The more rectangles you have, the narrower they are. So you have a certain amount of space in your interval. You have a whole lot more rectangles, so each one has to be narrower and narrower. So the logic is here, even if they don't start the same width, as you can see here in this diagram, they're growing. These intervals are wider over here than they were over here. But what he said is that's okay, because as the number of rectangles approaches infinity, they're all going to approach a width of 0. So since the limit is 0 of the width, it doesn't matter if they were the same to start with or not, because they're all going to the same value. So that was the reasoning behind why we don't have to have subintervals of equal width. Okay, there's one other thing that he opened it up for that we'll look at in a minute. The other thing that, or what this process then allowed us to do, is to define the intervals in such a way that when we did the sums, we were able to get things we could actually find. Okay? For example, here we have f of x equals the square root of x. Now, if we were to use our typical process with b minus a over n, and f of c sub I, where c sub I was the a plus the delta x times I. Eventually we would get down to the point where we had the sum from I equals 1 to n of the square root of I. Well, we don't have a formula for finding the sum of the square roots. We don't know how to do that. So instead, in this case here, what we did is we define our interval in terms of I squared, or as c sub I is I squared over n squared. There's a typo there, so you can change that from r to an n. Okay, so it's I squared over n squared. Now, this part right here, on a lot of these you'll be given this, okay? But this process right here is where there will be a little bit of trial and error if you were doing this and you weren't told what the interval had to be. Okay? You'd have to try some things until you got something that worked. So in this case, though, we're going to use I squared over n squared. Now, we still have a similar process that we're going to use. We're given c sub I, but we need to figure out delta x sub I. All right? Now notice here in the formula, it's not just a delta x, it's a delta x sub I. And that's because the delta x isn't the same for every rectangle. Okay? So we have to figure out what this is. And that's where we can use the c sub I to help us out. If c sub I is the right endpoint of the partition given by in these rectangles or these partitions, okay, a partition is just a separated part. So each rectangle we could consider a partition. I can find out how wide that partition is by taking the right endpoint of that partition and subtracting the right endpoint of the previous partition. Okay? So the right endpoint of this partition is I squared over n squared. I'm going to subtract the right endpoint of the previous partition. So instead of an I, it's going to be I minus 1. Okay? That'll give me the endpoint of the previous partition. So now we do a little bit of simplifying here. We FOIL that and do the subtraction. We get I squared minus I squared plus 2I minus 1 all over n squared. Okay? And of course, the I squared minus I squared is 0, so delta x sub I is simply 2I minus 1 over n squared. Okay? Is everyone with me so far?
So how did, I know it says c sub I is I squared over n squared, but how come you knew that delta x sub I is the same thing as c sub I?
Well, it's not the same thing. It's the delta x sub I is the width of the partition, or the rectangle, right?
The first one, or like what?
Of any of them. See, notice here, we're defining it in terms of I.
Oh, okay.
So we can find the width of any of the partitions by plugging in a different value for I.
Are we given that, or like, are we going to figure out that?
You'd have to figure out the delta x sub I.
But it's going to tell you that it's I squared over n squared?
Yeah, we're usually given what c sub I is in these cases here. Okay? We may figure some out on our own eventually, but... Alright, so the other thing that we need for our formula is the f of c sub I. Okay? Well, f of x is the square root of x, so f of c sub I is going to be the square root of c sub I, and we already know c sub I is I squared over n squared. So that just comes out to be I over n. And now we have everything that we need to approximate the area using this limit formula. Okay? So we have the limit as the number of partitions approaches infinity of the sum of I equals 1 to n of f of c sub I over n, times delta x sub I, 2I minus 1 over n squared. Okay? Are there any questions about anything that we've done up to this point? All right. So now, as we have with our other sums, I'm going to simplify what's inside, and I'm going to pull out the constant. What's the constant in this case?
N.
1 over n cubed. We've got an n and an n squared in the bottom. It's multiplied. So we can pull out a 1 over n cubed. So limit as n approaches infinity of 1 over n cubed times the sum from I equals 1 to n of, it's a 2i squared minus I. Alright, I distributed the I into the 2i minus 1. Okay? Now we have it in terms of things that we have formulas for. Okay? So this is kind of nice. Now we can take limit as n approaches infinity of 1 over n cubed times the sum of the I squares is n times n plus 1 times 2n plus 1 all over 6, but it's 2i squared, so I'm going to put 2 times that. Okay? So it's 2 times n plus 1 times 2n plus 1 all over 6. Okay? Then I have minus the sum of the i's. Well, we have a formula for that too. N times n plus 1 over 2. Okay? Now at this point we just got some algebra and then we can take the limit. So we're going to take the limit as n approaches infinity. I'm going to simplify and distribute that 1 over n cubed back in all at once here. So what we're going to have is this is going to be over 6n cubed. This is going to be a 4n cubed plus some other stuff. Now, we'll go ahead and find it, but understand here, since I'm taking the limit as n approaches infinity, the rest of my numerator really doesn't matter, right? Because all we look at is the leading coefficients. Okay? We should, yeah, just to be nice, it would be nice to go ahead and write it. So that's going to be a 3n times 2n. That's going to be a plus 6n squared plus 2n. Alright, and then minus, this is going to be an n squared plus n over 2n cubed. Okay? So what's the limit as n approaches infinity of that first fraction? Yeah, it's 2/3. 4 over 6 is 2/3. What's the limit as n approaches infinity of the second part? 0, because it's bigger on bottom. Okay? Here it's the same, so we do the ratio of the coefficients, 4 over 6. Here it's bigger on bottom, so it's 0. So our whole area comes out to 2/3. Okay? So you'll notice 90% of this process is the same as what we've been doing. The new part is really just the fact that it's not, you got to figure out what the delta x sub I is. Okay, that's really the new part on this. Okay, any other questions? Now here at the bottom you can see the comment that's made here. The reason this particular partition gave the proper area is that when n increases, the width of the largest subinterval approaches 0. That's what we started out by saying, is what Riemann realized is that it doesn't matter how wide they are to begin with, they're all going to approach a width of 0, so the width can be anything to start. Okay? Now, let's talk about what a Riemann sum is by definition here, okay? It says here, let f be defined on the closed interval from a to b, and let delta be a partition of a to b, given by a equaling x sub 0, which is less than x sub 1, which is less than x sub 2, which is less than x sub 3, all the way up to when we get to x sub n. And that is b, okay? So notice these x's are all the ends of the partitions. X sub 0 is a, x sub n is b, and then x sub 1 through whatever are all the ends of the partitions in the interval, okay? And it also says where delta x sub I is the width of the ith subinterval. That's what we had to figure out up above. If c sub I is any point in the ith subinterval, then the sum from I equals 1 to n of f of c sub I times delta x sub I is called the Riemann sum for f for the partition delta. So what we just did up above is we took the limit of the Riemann sum as n approached infinity. and that is what gave us the area. Okay? Now, there's a couple of terms here that you need to be familiar with. Before we get to those, though, one thing I want you to notice is that this is another thing that's different from what we've been doing the last few lessons. Notice that we don't require that f is non-negative. Okay, before, all the graphs that we worked with had to be above the x-axis. Now we're going to be able to deal with ones that are below the x-axis as well. Okay? So, that's just one thing. It's not here, but you may miss the fact that it was there before. So I wanted to point that out. So let's talk about the width of this. The width of the largest subinterval in the interval from A to B is delta, and it's called the norm of the partition. Okay, so the one above, you saw that they started out really narrow, and then they got bigger the further you went. So that last one, the width of that was the norm of the partition. And we have notation for this, which is right here, the magnitude of delta, or the norm of the partition. Okay? Now, if every subinterval is of equal width, well, that's what we've been dealing with. You have the norm equal to b minus a over n. However, what we're dealing with now, we don't know exactly what it is, but if we know what the biggest one is, then b minus a divided by the norm has to be less than the number of rectangles. Okay? That's going to be a general partition there. Okay? And this is just kind of bringing us to understand what Riemann observed. As the norm of the partition approaches 0, the number of subintervals approaches infinity. Okay? And that means that as the norm, if the norm is approaching 0, that implies automatically that the number of our rectangles is approaching infinity. Okay? The norm is this that we just said here, the largest subinterval of the partition. So the partition is delta. The largest subinterval has a width of that. Okay? Now, a lot of this is kind of technical stuff here, but it's all kind of building the basis of what we're working on. Okay? So we have this Riemann sum. So how do we use it? Well, here is the definition of a definite integral. This is simply another way of writing what we looked at before. Instead of the limit as n approaches infinity, we can say the limit as the norm approaches 0 of the Riemann sum. Okay? As long as that limit exists, then there are two things. First of all, f is integrable. Okay? That's kind of a weird word. All that means is that we are able to integrate it. Okay? That's all integrable means. We are able to integrate on that interval. And also we denote the limit. Instead of writing all this mess here, we have this notation here. You see the integration symbol? And this is what's known as the definite integral, because we have ends to the interval that we're going to look at, and it will give us a definite value at the end, rather than just an expression with the integration we were looking at before. Okay? So we have right here, this is the integral from a to b of f of x dx. That's how you would read that. The definite integral from a to b of f of x dx. Okay? Notice here, a, the left side of our interval, is written on the bottom, and that's what's known as the lower limit of integration. Okay? That's the lower limit. Let me fix that. The lower limit of integration. The number b is written up here on the top, And that's the right-hand side of your interval, so it's a higher number. That's the upper limit of integration, okay? And unless we're doing something a little weird, a is always going to be less than b, okay? So, here's one big takeaway that you need to have here. When we were doing the antiderivative, which is also known as the indefinite integral, we always got some kind of an expression, all right? Or a function that we could then graph or we could then figure out, okay? But it was always a function. It was some kind of a thing that still had the variables in it. When you do a definite integral, your final answer should just be a number. No more variables in it, it's just a number. Just like what we got up above, we got the answer 2/3 for our area. That's what you're going to get with a definite integral, okay? So that is, that's the big idea there, okay? Yes?
So if we had found the antiderivative and then you plugged in like the a and the b, does that become the integral?
There actually is something called the fundamental theorem of calculus. We're going to start looking at that on Tuesday. And essentially that is what you do. You find the antiderivative, and you're going to plug in b, and then you're going to take the same thing and plug in a, and you actually end up subtracting them. And that's the fundamental theorem of calculus. That will give you the area. And it's going to be a whole lot nicer than having to do all the Riemann sums all the time. Okay, but we do need to learn how to do Riemann sums too, because as we'll see, integrals, there's not always a nice way of doing it. Like there were derivatives. No matter how complex the function, we could still use like product, quotient, chain rule to figure it out. It's not the same with integrals. It's kind of challenging. So that's why you need to know these ways of getting it other ways, or at least getting a good approximation other ways. So, all right, one last thing here, and then I want to look at a couple of the problems just to introduce what you'll be doing on the homework, and then I'm going to let you guys start on that. One last thing here is if it's continuous, then it is integrable. Okay? Notice it's allowed to have points on it, unlike derivatives. Okay? And with the derivative, if it wasn't smooth, then you couldn't take the derivative. Here, it's okay to have those sharp turns or points on them. As long as it is continuous on the interval, we can take the integral. Okay? So that's the last idea we had there. Alright, so I want to look at one of the ones from homework just because we only did one example. Okay, but I wanted to look at one more here just to make sure we understand this pretty well. And then also, this part over here, they're asking you to set up definite integrals on numbers 13, 15, and 17. These are from the homework that you'll be doing. I wanted to do one of these just so you guys understand. And we'll actually go ahead and do that first, and then we'll get to the others. So here, we're setting up a definite integral that yields the area of the region. Okay, so you're given the function, in the case of number 14, it's the function f of x is 4 minus 2x. Now, if you are asked to find area for this, what would you do?
Base times height.
Base times height divided by 2, right? You know, hopefully you wouldn't be delving into too much calculus to do this one. All right? So, base times height divided by 2, 2 times 4 over 2, the area would simply be 4 square units. Okay? Now, we could do this with an integral, though. It'd be the integral of f of x, 4 minus 2x, dx. What would we use for the a and the b, the lower bound and upper bound, though?
0 to 2.
0 to 2. So we have the integral from 0 to 2 of 4 minus 2x dx. If you knew the fundamental theorem of calculus already and evaluated that integral, guess what you would get? 4. All right? So it does actually end up equaling 4. All right? You do not have to do that on these ones, although you could on 13 and 15. But that's what you would do with these, okay? Here on 16, we would take the integral of x squared dx from 0 to 2. This one, there isn't a good way of doing it geometrically because that's a curve. It's not just a triangle. We don't have a formula for that. But once we learn how to do the integrals, we'll be able to, okay? This is all you need to do for 13, 15, 17 is write out those definite integrals. We want to get a good idea of the notation there and what it means. All right, so here we're going to move over here to this one. We're going to use the example that we did before to get the area bounded by square root of x, the x-axis, 0 and 3. Alright, so you can see here that c sub I is given to us. Alright, so like we did before, we need to figure out f of c sub I and also what delta x sub I is going to be. Alright, so let's start with f of c sub I. What's that going to give us? What?
3i over n.
Close. Well, it's the square root of 3i squared over n squared.
The square root of 3i.
There we go. Square root of 3 times I over n. Okay? So we got the square root of 3 times I over n. Okay? So now we have to do delta x sub I. How do we find that?
Is it the same thing?
You just like minus I minus 1.
Okay. We're not going to use the f of c sub I though. We're going to use the c sub I. All right, but you got the right idea. We're going to do what we were given, so 3i squared over n squared minus the same thing with an I minus 1.
So do you always do that? You do ci minus.
C sub I minus 1, yeah. If you remember in the formula that we were given, the delta x sub I, or I should say c sub I, was always some value between, or I'm sorry, not c sub I. The point that we were using, whatever point we were using, was always between c sub I and c sub I minus 1. So the width of that would be the one end minus the other.
Oh, so okay.
Okay? Alright, so we just need to simplify a bit here. We need to FOIL 3i squared minus 3i squared plus 6i minus 3 all over n squared. And the 3i squared minus 3i squared cancel out, and we have 6i minus 3 over n squared. So now we're ready to set up our sum. Using the limit as n approaches infinity of the sum from I equals 1 to n, this is our Riemann sum here, of f of c sub I, that's root 3 times I over n times delta x sub I, 6i minus 3 over n squared. So we want to pull out the, let's pull out the constant. What constant could we pull out? Square root of 3 over n cubed. Yeah, that'll work. So now we're taking the sum from I equals 1 to n of I times 6i minus 3, right? Or 6i squared minus 3i. Okay?
Is it over n?
Well, no, I took out an n cubed, so all these n's here are gone. I took out the radical 3,
I thought it was
so this is all I've got left. Okay? Now we're down to stuff that we have formulas for. Again, every one of these sums, you're trying to get it so that you're taking the sum of an I squared or an I cubed. Because that's all we have formulas for. So now, we can do this. We've got the limit as n approaches infinity of root 3 over n cubed times 6 times the formula for I squared. So that's n times n plus 1 times 2n plus 1 over 6, which is kind of nice because the 6's are going to cancel here, minus 3 times the sum of the i's. Well, that's n times n plus 1 over 2. Okay? Now all we have to do is simplify a little bit so we can take the limit. Okay? So we have the top, 2n cubed plus 3n squared plus n. And that's all going to be times a root 3. So root 3 times that all over n cubed minus, this is going to be 3 times the root 3 n squared plus 3 root 3 n, and that's going to be over 2n cubed. Now I don't need to get a common denominator or anything like that because I can take the limit of each part separately. Okay? So what is the first part going to come out to? 2 root 3 over 1, yeah. Okay, so this is 2 root 3. We've got this. These are the same. Okay, and that's just over the coefficient 1 there. I don't need to bother distributing the root 3 to the other parts because they're irrelevant here. But then I subtract, what's the limit as n approaches infinity of the second half? 0, because this is bigger, so this is all 0. Excuse me, thanks. So this is just 2 root 3. Okay? So you can work through these. You have some other examples to try for your homework. I'll let you use any time that we've got left to start on these. Okay? But take your time. Some of the homework you'll be able to just write down answers for. It'll be pretty easy. Other stuff that you'll have to do a little bit more work for. Okay? But take your time, check your work, and come with questions tomorrow. All right? All right.